This is Algebra Lesson 7-8, Geometric Sequences. We've done arithmetic sequences in the past, so now today we're going to take a look at geometric sequences. A geometric sequence is a sequence in which the ratio between consecutive terms is constant. So with an arithmetic sequence, you are always adding or subtracting the same number. With a geometric sequence, you're either multiplying or dividing by the same number. The common ratio is the constant ratio between terms in a geometric sequence. So there are two ways to write a geometric sequence. Okay, a geometric sequence with a starting value a and a common ratio r is a sequence of the form a, ar, ar to the second power, ar to the third power, and so on. The recursive definition has two parts. You always have to give the initial condition first, which means you have to give them the starting formula. So if a sequence started with 6, then a to the first would be 6. And then you give the a to the nth power equals a to the n minus 1 times r for n being greater than or equal to 2, because you always start on the second number of the sequence. The explicit definition for this sequence has one formula. You just do a of n is going to equal a of 1, which is your first term, times your common ratio to the n minus 1 power, where n is greater than or equal to 1. Okay. For every geometric sequence has a starting value and a common ratio. The starting value and the common ratio define a unique geometric sequence, and we'll talk about that. So the first thing we need to be able to do is we need to be able to identify geometric sequences, which means you need to be able to find the common ratio. And sometimes that's really, really easy, and sometimes that's really, really hard. The easiest way to find it is to find the common ratio. You write each term over the term to its left, and you simplify it. Okay, so you write the second term over the first term, and then the third term over the second term, and so on and so forth. So for this first sequence, we have 3, negative 15, 75, negative 375. So, okay, since there is no term to the left of the 3, we can't start with that one, but we can start with the negative 15, and you divide that by 3, and that becomes negative 5. Okay, then you do then you're going to go to the next term, so you're going to go 75 divided by negative 15. That is also negative 5. And then last but not least, negative 375 divided by 75, which is also negative 5. You should check all the terms to make sure that it stays geometric, because every once in a while you can start off with something that looks like it's geometric, but then the third number in could all of a sudden have a different ratio, which means it goes out of being geometric. So the common ratio for this sequence is negative 5, which makes sense, because if I took 3 and I multiplied it by negative 5, I get negative 15. Negative 15 times negative 5 gives me positive 75. 75 times negative 5 gives me negative 375. Okay, on this second sequence, again, you're going to take the second term and write it over the first term. Okay. So we're going to take 150 and write it over 750. And you might go, wow, that is weird. Yeah, because this one's going to be a fraction. 150 over 750 reduces to being 1/5. And then I'm going to take 30 over 150, which is 3 over 15, which also reduces to 1/5. And then I'm going to take 6 over 30, which reduces to 1/5, which means the common ratio here is 1/5. To get from 750 to 150, I have to multiply 750 by 1/5. Okay, even though you can divide it by 5, because the formula is dealing with multiplication, we always talk about the common ratio as a multiplied number rather than a divided number. So instead of saying we're going to take 750 and divide by 5, and then 150 and divide by 5, and then 30 and divide by 5, we're taking 750 and multiplying it by 1/5. 150 multiplied by 1/5, and then 30 multiplied by 1/5, so on and so forth. Okay, let's look at number 3 here. Okay, 4, 6, 9, 13.5. So if we do write second over first, that's 6 over 4. If I reduce that, so that's 3/2. Okay, I'm going to leave it as 3/2 rather than 1.5, because it's just nicer that way. And I'm going to do 9 over 6. If I reduce that, 3 goes into 9 3 times, 3 goes into 6 twice. Then I'm going to do 13.5 over 9, which is the same thing as saying 135 over 90. Okay, which reduces to 3 over 2 again. Okay, so my ratio is 3 over 2. When you get fractions, they get a little bit more difficult. Many times students have a really hard time looking at the problem number 4 here and saying, I don't have the slightest idea what the common ratio is. Okay, so you're going to do 3 halves, and you're going to divide it by 3. Well, remember, dividing by a whole number is the same as multiplying by its reciprocal. So that's 3 halves divided by 3, which is 3 halves, times 1/3, which is 1/2. And if I take 3/4 and I divide that by 3 halves, that's the same thing as saying 3/4 divided by 3 halves. Remember, to divide a fraction, you multiply by its reciprocal, so 3/4 times 2/3. Okay, 2 goes into 4 twice, 3 goes into itself once, so it becomes 1/2. So the last one, you're going to have 3/8 divided by 3/4, which would be basically 3/8 times 4/3. I'm skipping the middle step. And you get 4/8, which is 1/2. So my common ratio here is 1/2. 3 times 1/2 is 3 halves. 3 halves times 1/2 is 3/4. 3/4 times, excuse me, 1/2 is 3/8. All right, you can look for a common difference or a common ratio to determine whether a number sequence is arithmetic or geometric. If there's no common difference or no common ratio, then the sequence is some other sequence. It's not geometric and it's not arithmetic, but it could be some other type of sequence. It doesn't mean it's not a sequence, it just means it's not an arithmetic sequence or not a geometric sequence. So let's take a look at a couple of these problems. We're going to determine whether these sequences are arithmetic or geometric. Fine. 2 to 4, 4 to 6, 6 to 8. So we're adding 2, adding 2, adding 2. So we have a common difference. Okay, so if I have a common difference, that means it is arithmetic. My handwriting's not very good right there. All right, 2 to 4, 4 to 8, 8 to 16. Well, 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. We have a common ratio, okay, because we're going to go 4/2, which is 2. 8/4, which is 2. Okay, we know the common ratio is 2, so since it has a common ratio, it must be geometric. Number 7 here, 162 to 54, 54 to 18, 18 to 6. Well, I know we're not adding or subtracting the same number because 162 down to 54 is not the same as 18 and 6. Okay? To go from 6 and 18, you're adding 12. To go from 54 to 162, you are not adding 12. Okay? So if it's going to be anything, it's going to be geometric, so I need to look at my common ratio. So 54 over 162, if I reduce that fraction, I get 1/3. If I go 18 over 54, reduce that fraction, I get 1/3. If I do 6, sorry, I messed that up. 18 over 54, now I'm going to do 6 over 18, which is also 1/3. Since it has a common ratio, it would be geometric. All right, number 8 here, 98 to 101, 101 to 104, 104 to 107. Well, I know we have to be adding or subtracting. 98 to 101, we add 3. 101 to 104, we add 3. 104 to 107, we add 3. So it has a common difference. So it has to be arithmetic. So it is an arithmetic sequence. Now, if it wasn't either geometric or arithmetic, you would say neither. You would just say that it is neither a geometric sequence nor an arithmetic sequence. Okay. Any geometric sequence can be written with both an explicit and a recursive formula. The recursive formula is useful Okay, the recursive formula is useful for finding the next term in the sequence if you only have to find one or two terms. The explicit formula is more convenient if you need to find any term, the nth term, the first term, the sixth term, the 12th term. I will focus more on the explicit formula. I will teach the recursive formula, we'll practice it a little bit, but I'm going to focus more on the explicit formula because the explicit formula is more helpful and I think more useful. So, problem number 9 is asking us to find both the recursive and the explicit formulas for the sequence 20, 30, 45, 67.5. So before we do anything, we have to find the common ratio. So if I look at this particular problem, if I take 30 and divide it by 20, I get 3/2. If I take 45 and divide it by 30, I still get 3/2. And if I take 67.5 and I divide that by 45, I still get 3/2. So my common ratio is 3/2. So to write the recursive formula, remember a recursive formula has two parts. You have to always tell me what the first term is. So a of 1 is equal to 20 because that's my first term. Then you have to use the formula. All right, so the formula is going to be a of n will equal a of n minus 1 times the common ratio, which in this case is 3/2. Not my favorite formula. It does work, but it can be a little confusing because you have to know what 1 is. I have to know that a of 1 is 20 in order to solve anything in this particular formula. The explicit formula allows me to get any number I need without having to have the number in front of it. Remember, the recursive formula requires you to have the previous number in order to get the next number. So if I needed the 5th number in the sequence, I would have to know what the 4th number was. And I would have to know what the 3rd number was, so on and so forth. But the explicit formula lets you go to any number in the sequence whenever you need to. And the explicit formula just says you take a of n, which is always whatever you're looking for, is going to be your first term, 20, and then you're going to multiply by your common ratio, which is, in this case, 3/2, to the n minus 1 power. All right. And we can put this one in parentheses too if it makes it easier to see. All right. The difference between the recursive and the explicit, the recursive has to have the first part where they tell you what the first term is, and you have to find all the preceding terms in front of it in order to find the next term, whereas the explicit formula allows you to go to any term you want, whenever you want. So let's take a look at using the explicit formula. We're going to find the first, 6th, and the 12th terms of each sequence. Okay, and this is written in the explicit formula, which is the formula I will normally use. So if I look at this first explicit formula, a of n equals 4 times 3 to the n minus 1. The first term should be easy. I shouldn't have to do anything. This is always the first term. I can double check it. If I wanted to find out if a of 1 actually equals 4, I would do 4 times 3 to the n, when this in this case is 1 minus 1. Well, anything to the, okay, so this is 4 times 3 to the 0 power. Anything to the 0 power is 1, so this is 4, which I told you I knew it had to be because that's the first term in the sequence. That's part of the recursive formula. Okay, the 6th term tells us we should do 4 times 3 to the 6 minus 1 power. So we're going to do 4 times 3 to the 5th power. Now remember, you must do your order of operations first. So here we're going to do 4 times 3 to the 5th power is 243. So now we're going to multiply 243 times 4 and we'll get 972. So the 6th term in my sequence is 972. And last but not least, I need to find the 12th term of my sequence. So the 12th term of my sequence is going to be 4 times 3 to the 12 minus 1. So that's going to be 4 times 3 to the 11th power. That's going to be a pretty big number. 3 to the 11th power, use my handy dandy calculator, is 177,147. And I multiply that by 4, and I'm going to get 708,588. So fairly large number there. Geometric sequences can get fairly large fairly quickly because you're multiplying versus adding. Let's take a look at the last problem. We're also going to find the first 6th and the 12th sequence. I'm going to find the first sequence first number without actually putting it in. A of 1 is going to equal -2 because that's the first number. It's part of the sequence. The 6th term of the sequence is going to be -2 times 5 to the 6 minus 1. So this is going to be -2 times 5 to the 5th power. So we have -2 times 5 to the 5th power. 5 to the 5th power is 3,125, so -2 times 3,125 is going to end up to be -6,250. So our 6th term is -6,250. And last but not least, our 12th term, A of 12, will equal -2 times 5 to the 12 minus 1, which is -2 times 5 to the 11th power. 5 to the 11th power is going to be a very large number. -2 times 48,828,125. And when you multiply that by -2, you're going to get -97,656,250. So there would be our 12th term of that particular sequence. So as you can clearly see, the recursive formula works for some things, but the explicit formula is much easier to use because you can get any term at any time as long as you have the explicit formula. All right, our closure question for this lesson. In what type of situations is it useful to use a recursive formula, and when is it more convenient to use the explicit formula? And I've explained this at least 3 times in this video, so you should have no problem answering this closure question.